Good evening, one and all. Good evening, sir. We are requesting, we are welcoming you, sir, and we are requesting you to please continue the sessions.
Good evening to all of you. I hope you can hear me.
Yes, sir.
Sir, we can hear you, sir.
Okay. And I hope you can see the slide also.
Yes, sir.
Yes, sir. Yes, sir.
Good. So thanks a lot because yesterday I requested for change in the schedule of my lecture because tomorrow I have to travel. Thanks to the organizers, they agreed. Today talk is centered around drag reduction, resistance when it comes to typical engineering structures. And when we say engineering structures, we normally talk about three from the ocean engineering perspective, and all of them fall under broad area of mechanical science. For example, we talk about car, we talk about aircraft, we talk about ship. So, in general, in the broader sense of mechanical sciences, there are three major structures which are dominated by drag. When we were discussing about the design, then we talked about how the design can be modularized, how you can think of design in terms of nose, parallel middle body, or the middle body, and the tail. And at that time, I mentioned briefly that nose is important for drag, middle body is important for payload, tail is important for propulsion, stability, power. And I also mentioned that the way it is fair affects the viscous pressure drag. So, drag or resistance will have two components. One is driven by the friction, the Reynolds number. Second is driven more by the Fruit's number. That's the viscous pressure drag. Frictional drag is dependent upon the surface area and the Reynolds number. Viscous pressure drag depends upon the Fruit number and how the structure is paired, how the nose is paired with middle body, how the middle body is paired with tail, and whether the body is full or fine or how the shape optimization has been done. Now, from the resistance optimization side, a lot of research has gone into exploring what actually is skin friction drag, why it is dependent on the skin, why it is called frictional drag, and so on and so forth. Major research has been conducted to find out different possibilities by which this friction can be reduced. And the reasons are obvious. You can think about it. When it comes to nose, we have restriction. When it comes to tail, we have restriction. We cannot have a nose which is very long. You cannot have a tail which is very long because that really doesn't give you any revenue. Similarly, when you design a car, you can have flexibility in designing the nose, long and narrow, tail which is full and long, but still the cost of car will go up. So very few cars, for example, BMW series, Mercedes series, they will have a very long and sleek body. But the same you cannot expect from Maruti because the cost is not really of that low. So this is something which has been tried quite a lot. And we should say with some degree of success. The friction resistance has been tackled. The gains have been reported. The full scale implementation has been tried. Not was very successful, but yes, in certain cases it has been put into practice. So today's lecture, we will be talking about the importance of drag in general, importance of frictional resistance, and what are the possible gains if you tackle that. What is the nature's role in generating surfaces which have low friction? And when you have low friction, you will get reduction in the drag. So this is also area which has gained importance in the last 20 years, that biological influences in the field of engineering are growing with every passing year. So you have stability concepts coming from biological sciences. You have propulsion concepts which are coming from biological sciences. You have other computing philosophies which are coming from biology. Modeling, DNA computing coming from biology. So drag is also somewhere biological influences can be found. Drag reduction mechanisms can be classified broadly into two categories: passive and active drag reduction, and whether they are supported by the experimental investigations. And finally, some concluding remarks. Now, because we deal with ship, so majority of the focus will be on ship, but other areas will also be touched slightly. But because we are involved in research related to ship science and have considerable experience, so we will be devoting more time to the problems associated with ship structures. Now, broadly, if we see the total resistance, it will have two components: residual resistance and skin friction resistance. Residual resistance is because of viscosity, pressure. It is also called viscous pressure drag because of velocity. It can also be termed as what we call pressure resistance. Pressure resistance will have two components: wave resistance and the viscous pressure resistance. Wave resistance will be further classified into wave making and wave breaking. And viscous pressure resistance will be coming into what we call viscous resistance. Now, residual resistance means that one component in the skin friction will also come because of velocity, and it is dependent on the Reynolds number. And that gives rise to what we call broadly the friction resistance or frictional resistance or skin friction drag or skin friction resistance, etc. So the idea is that how this component can be reduced, because this dominates pretty high at the low velocity. As the velocity increases, the component will dominate from the residual resistance side. That means the wave resistance will dominate, the viscous pressure resistance will dominate. But this will remain in some percentage, and this percentage is significant. This is dependent upon the velocity. This is also dependent on the velocity through Reynolds number. But here, the chances of you getting significant gain is very low. And there are three reasons for that. One is, if you want to improve the wave resistance, then you have to generate a shape which is conventionally narrow. And if you have a narrow shape, which is used basically for high speed ships, wave piercing hull, you do not get volume. And if you do not get volume, you don't get payload. And if you don't get payload, then what is the purpose of ship? Frictional resistance is something which is related to the surface area. And here, the idea is not really to reduce the surface area, but the idea is that surface to surface contact can be altered, can be changed, can be modified, and through that, the friction resistance can be tackled. Now, why the field is important? Because the possibility of significant gains is very large, very impressive, especially when it comes to slow speed ships, especially when it comes to ships with very high block coefficient. For example, oil tankers. And our world, our economy, our progress, our development depends on oil and gas. And oil and gas ships are always with high block coefficient. That also we were discussing in some detail few days before. Once you gain something on friction resistance, the same will be reflected in energy savings. And when you have energy savings, you will have lower emissions also because you need less power to run your ship at a particular speed. The performance can be guaranteed at slightly lower speed range, but the research is also looking at the challenges of high speed requirement. For example, what happens when the yachts are reaching? That means boats are running at high speed, and naval ships, which are of fine block coefficient but runs at very high speed. Now, the friction resistance is written as CF multiplied by half rho SV square. S is the surface area, rho is the density of water, CF is the frictional coefficient, is frictional resistance coefficient. Now, from this, if we look at the ways by which it can be reduced, the first possibility is that reduce CF. Second possibility is reduce the fluid density. And third is reduce the wetted surface area. Reduce the ship speed. The catch is, except the first one, others are either not in your hand or the economics doesn't allow it. For example, reduce fluid density. Fluid density. You are running in water, and that water is lake water, sea water, canal, river, depending upon what kind of business you have. So you have no control on the water density. Wetted surface area is coming because of the nature of the ship, whether it is full or fine. That also is governed by the economics, so we have no control. Ship speed, again, it is governed by the economics. We have no control. So accept this first one, that is reduce the friction coefficient. We have no way by which friction resistance can be reduced. And this is something which has to be investigated. What are the ways by which the frictional coefficient can be reduced? Now, the very first idea is to look at the nature. What happens when you have big sharks running, moving from one place to another place? They can propel themselves with very low power. They can turn within a fraction of their length. On the other hand, ship will take 3 to 7 times of the length. That means the turning of a fish is much more efficient So all these characteristics have motivated people to see, is there anything special or anything different on the skin of a fish. And that's what promoted the first idea that shark will have some scales, and these scales are basically consisting of microstructures. So the first idea is that can we use these microstructures to reduce the drag? And you can see here the microstructures. People also investigated the dolphin skin, and they found that it has a compliant skin. Compliant skin means skin which ensures the flow doesn't remain compliant to its boundary layer. So one way you are looking at microstructures to reduce the drag. In the other possibility, you are looking at the ways by which the boundary flow or the flow at the boundary or the boundary conditions or the boundary layer can be changed. What should be done when it comes to microstructures? So first, we should get some idea about what kind of groove, what kind of structures, what kind of dimples we need to generate. So the first investigation started with grooves that are aligned with the flow. So if you see the top view, the grooves are aligned with the flow. Then people also investigated grooves which are arranged at 45-degree tilt, that is 45-degree tilt angle. The idea is that they will change the nature of flow. They will affect the generation of turbulence. They will reduce turbulence. They will reduce drag. And because they are affecting turbulence, they are reducing turbulence, they will also have some property, favorable property in the field of anti-fouling and self-cleaning. Now, whenever you have a structure which is protruding outward from the skin, from the base, over a period of time, you will have biofouling. And if the structure is not of sufficient, or if the microstructure is not of sufficient width and height, the cleaning of this will become difficult because of fouling. So it is important for us to also check during the time of investigation that do we have the possibility of utilizing these microstructures for the property of anti-fouling and self-cleaning. Now, as a rule of thumb, higher wetted surface will generate higher drag. So one way to look at it is that can you reduce the wetted surface? Now look at the turbulent boundary layer. You have the different regions, viscous sublayer, buffer sublayer, logarithmic layer, and then the wake, outer regions. And we have also shown the number of cases where it can happen. Reynolds number range, where it will dominate, lower Reynolds number range, and the higher Reynolds number range. Viscous sublayer is the place where you have the dominance of friction coming primarily because of the viscosity. Then we have a layer, buffer layer, where the flow changes from one way to other. There it is more intermixing. and then you have more and more drag which comes because of turbulence. Buffer layer is something which is most dynamic portion of the boundary layer. The turbulence will peak over it. It will also have what we call peak turbulent kinetic energy. Flow in the buffer layer is dominated by streamwise vortices. And all these concepts, for example, turbulent modeling, the total amount of turbulent kinetic energy available, peak turbulence protection are utilized in designing systems which will alter the basic flow characteristics. Flow in the buffer layer, as I told, is dominated by vertical structure. Streamwise vortices is one class of it. Second class is the coherent structures. The idea is to extract the mean flow and look at the energy which is inherent in the mean flow. To extract energy from the mean flow. Also understand that this concept of vorticity is important when we deal with what is called flow over the wing, flow over the wingspan, flow over the aerofoil wings. There it plays a very important role. High speed fluid will move close to the wall and this higher mixing momentum transfer basically lead to higher drag. So in general, when we talk about mixing, when we talk about momentum transfer, when we talk about turbulence, when we talk about bursting of bubbles, when we talk about cavitation, all of them are likely to increase the drag. So here, especially in the buffer layer, it is not because of viscosity, because viscosity dominates at the lower Reynolds number range. The higher mixing and momentum transfer will lead to the higher drag. So one is that we understand what is happening in the flow from the boundary layer theory. The next structure to think about is how can you change the nature of flow? And this is important for all of you to know that the future belongs to flow control devices or flow control mechanism or flow control engineering. So every major industry, whether it is aircraft industry, aerospace industry, whether it is ship, naval architecture, whether it is cars, all of them are investigating structures at all three levels: micro, mini, and the major, which can change the nature of the nature of flow. So one structure which is at the mini to micro level is called riblet, and you can see here the blade riblets. Distance between the two riblets is S. Thickness of the riblet is T. Height of the riblet is H. And depending upon these ratios, H, T, and S, you can get different scales. You can get a shark scale. You can get a scallop riblet, and you can get a sawtooth riblet. Now, three things are pretty obvious from here. This is a flow control device, first. Second, the idea is to generate grooves which are parallel to the flow. That means this should be aligned with the flow. Third, they are mini to microstructures only. They are not major structures. You cannot use them in few meters. You can use them only up to few microns to few millimeters. Role of riblet, essentially what happens, and this is taken from the paper. In most of the slides, I have given the reference below so that people who want to follow it, they can follow it up later. So, what is the role of riblet? The first is pretty simple that it alters the nature of flow. It is the first major flow control microstructure. What happens from the mechanics side? It reduces the streamwise vortices. And when you have the structure which is reducing the streamwise vortices at the generation level itself, you have very little momentum transfer. Vortices will interact only with the riblet tips. And because there is no momentum transfer, the drag will reduce. Because we are looking at the turbulence range or what is called the mixing range. Low velocity fluid will always exist in the valley. So here, if we see, this is the valley. Low velocity will always generate low drag, low friction drag. So see here, the streamwise vortices affected by the reflective. It has been shown at 3 meter per second. Drag decreasing case. This is a flat plate. This is the advantages of reflex. What has been achieved. Very successful experimental and field investigation. It has been implemented quite successfully in the field of aircrafts, racing yards, and the riblets are basically from vinyl film. The maximum advantage has been reported around 10%, which is significant. The maximum drag reduction is possible around 10%, and that depends upon the blade geometry. Now, what are the issues? Now, think about it. When you have a structure which is protruding outward from the skin or from the base, these areas will always have accumulation of bioalgae, fouling, and over a period of time, fouling may affect the structural integrity, and fouling itself will increase the drag. So this is what has been reported. Different like H by S ratios and all that. So this particular graph can be explored by people who have further interest in this area. And you can see that the H by S plays an important role. Similarly, thickness also plays an important role. And thickness is also important from one more perspective that thickness should not be too low, otherwise, with the flow pressure or with the force coming because of a particular flow velocity, the riblet will have a tendency to bend. And if the thickness is low, it can bend permanently. It can have plastic deformation. So it is important for us to understand that the thickness is important from the structural point of view also. Similarly, T by H. That means what is the span and what is the T. There is a structural component also coming into picture because it acts like a cantilever. And cantilever will always have very high deflection at the tip. This is something which I also discussed in the very first lecture, that please do not make the mistake of thinking fluid mechanics only in terms of fluid mechanics. When it comes to application of fluid mechanics, it will always be combined with a couple of other mechanical science. For example, here it is also combined with structural mechanics. Otherwise, your flow control device will have other structural related issues. Now, next pupil thought is that you basically have a surface of the ship or the surface of aircraft or car basically moving in a fluid, in a fluid medium. And this fluid medium is also generating a surface. So you can have a car moving in an enclosure of air. You can have ship which is moving at the interface of air and water. So you can have one air space, one water space, it is moving. So the idea is that when we talk about skin friction, can we think this in terms of movement of two surfaces against each other, movement of two spaces against each other, or to a broader thinking, movement of two materials over each other? When we say two materials over each other, then we can think in terms of solid with gas, solid with water, all kind of possibilities. Now, this has given rise to approaches which are governed by lubrication effect and all that. So before we come to that, the second is, can you change the generation of vortices, generation of basic fluid flow around the body by changing the nature of fluid? For example, you may have fluid which is a mixture of gas and water. You may have pure gas, you may have pure water, or you may have a combination of water and. Then the question is that, do you have the possibility of injecting polymers which are coming from purely from organic sciences, rarely from inorganic sciences? And organic and inorganic is because you have to maintain certain level of biodegradability. Can you change the basic nature of the fluid in which the body is operating through polymer injection? And that is something which affects what we call coherent vortex. It affects the basic modulus, and that is shear modulus of elasticity, the basic fundamental properties, molecular binding, etc. What is the beauty of this? It is changing the nature of flow by changing the basic composition of the fluid, between the structure and the fluid. So the long chain polymers disrupt the near wall vortical structure. That means what is happening close to the wall, the long chain polymers will form a protective layer around the wall, and that will alter your near wall vertical structures. Now, recall the previous slide. The vertical flow or the vertical formation of or the vertical momentum transfer because of the vertices. They are the major ones contributing to the drag. So if you have a protective layer around the wall or near the wall, which is disrupting or discouraging the formation of vertices, in that case, a part of the problem will be solved. Viscoelasticity time scale will match the turbulent fluctuations. The concept has been well established for internal flows, for example, pipe, channel flows. As, uh, as the research indicates, the drag reduction can actually go very high, up to 70%, has been demonstrated, but only at the pipe level, the channel flow, not with the real structures of high importance. Problems in case of external flow, that means when we are talking about flow over an aircraft, flow over a ship, this technique has a limitation. But within the concept of pipe, within the concept of channels, it has been shown to be very effective. Now, why can't we apply it to ship or aircraft? Because the idea is to keep the very high concentration near the wall, which is not going to happen. It's difficult. The surface area is too large. The velocity of water over it is also significantly large. There are other flow disturbances. Only near wall concentration matters, not really. In case of aircraft and ship, it really doesn't offer cost benefit. So the polymer injection has a limited use in the case of structures of external flow, like ship, aircraft, even cars. Other idea which came into picture around 20 years before is called large eddy brake. And the idea is very simple. Again, look at the graph, see viscous sublayer, buffer sublayer, logarithmic sublayer, weight, and think what are the ways by which skin friction can be manipulated, not from the portion which is close to the wall, near wall, but outside the boundary. That means at the higher and higher reload sum. So from the outer portion of the boundary layer, investigate, think, explore ideas by which you can interfere with the largest eddies. And when you are able to break them, when you are able to develop a technique which is exploring, implementing the break of large eddies in the outer layer, you will be able to achieve reduction in the friction, reduction in the drag. Larger eddies in the outer layer, when they are when they are broken, they will also reduce the frictional drag downstream. Up to 30% drag reduction has been reported, but there is a case of increased drag on the device itself. That means when you talk about the devices, they will have the increase. Drag. So net reduction is around 9 to minus 5%. It is also sensitive to direction of flow. Now, this is something very important. Please understand that when we talk about riblets, I told that they are from micro to mini size. The problem with large eddy brake is that they are from mini size. And when you have structures which are protruding outward significantly, they act like appendages. It's a fairly well-known concept in the field of vehicle design that any appendages to the body will adversely affect the drag. So if you have a bare hull drag and you add on different appendages, with all appendages, your actual drag may be 100%, 150%, 200% higher than the bare hull drag. That means the appendages will add to the drag approximately 100% to 200%. That is actually happening here also. And it is also dependent on the size of the appendage. If you are maintaining the micro and mini size, then the increase is not significant. But when it comes to mini size, the large eddy breakers, which you normally use, then the device will add to the drag because it's appendage, and that drag is significant. And that will cross this 30 to 20. So out of 30, if 20 is gone, it becomes only 10. And if you keep on increasing it, then it becomes 35. So 30 minus 35 minus 5. So that's what we are trying to make you understand is that, see, the height is like 1 mm, 2 mm, 4 mm, 2.5 mm. Significant. Span-wise spacing, again 2 mm, 4 mm, like that. The chord length, again 5 mm. So you are talking about the structures which are a few millimeter by few millimeter by few millimeter. And that's something which can break eddies in the outer layer of the boundary, outer portion of the boundary there. But it will also add to the exposed surface area. And the more surface area you have, more drag you have. So this is the concept which has been investigated in the preliminary phases, not in the final phases. So people are still trying to understand what should be the ideal mechanism. Because the moment you have height significant, there are other structural difficulties. So it's a concept which is difficult to implement and difficult to optimize, difficult to be put into practice. Other idea which people have been fascinated with is that when you see a drop falling on a lotus, or when a raindrop falls on leaves of rose flower, you will feel that it really, the leaf or the surface doesn't get wet. It remains as a drop. And the drop remains as a drop without breaking. It remains in a particular shape with particular size. That motivated people to see what is so special about the leaves of lotus or leaves of most of the flowers. Then they found that this is something related to hydrophobic. That means the structure is not really loving water. It is something which is able to repel water. It also has remarkable self-cleaning characteristics. And this allowed people to see what is so special in the lotus leaves. And they found that it has a what we call it has what we call hierarchical structure, a combination of microscaling and nanoscaling. That means you have kind of protrusions, kind of uh, uh, microstructures, mini structures, nanostructures of different shape and different size. And then think of that and try to put the water drop on it. And you will find that the water drop looks like this. So there is no contact of water drop with the surface because these are micro, mini, nano protrusions which are present on the skin or on the base. And at a certain angle, they have, which really doesn't allow the droplet or the drop to sit on a structure which is flat. So this is giving rise to what we call hydrophobic behavior of lotus leaves. Now, can we go one step further and say, okay, let's investigate super hydrophobic surfaces, SHS. Think about the angle, and instead of saying that it's a pointed thing, let's make the top flat and see how the sleep angle is maintained or how the wetting angle is maintained. So super hydrophobic the surfaces, they have a wetting contact angle which is greater than 150 degrees. Think about the air pockets, think about the solids, and think about what is called slip length. Tens of micron of slip length is this, and you will have quite large numbers. They will result into non-negligible reduction in the shear stress. But because it is not coming in contact with the surface itself, there is no skin to skin contact. And if there is no skin to skin contact over a larger skin area, because here, if you see the droplet or the drop is coming into contact with the skin over a very little area. It was much better when it was pointed, but here it is still better because there is no skin to skin contact or there is a very little skin to skin contact. There will be significant reduction in the skin frictional drag. Now, the good thing is it is possible within the manufacturing limits, within the manufacturing capabilities, to design and fabricate such surfaces using micro and nanostructures. But think about it, it is at the level of micro and nano. Riblets, which we talked about today, they were at the level of mini and micro. Similarly, the large eddy breakers, which we talked about, they are the level of mini. Possible gains and difficulties. What is so special? What makes them so interesting? 20 to 30% drag reduction at even higher errors number, 10 to the power 6 and 10 to the power 7. Surface roughness should be smaller than viscous sublayer. And that is something which is not easy to achieve. Because when you talk about the manufacturing accuracy and manufacturing requirement, and the moment you start reducing it from meter to millimeter to micron to nano to pico, the manufacturing difficulty increases. And when you talk about fluid, which is coming with a velocity, which is coming with a force, then the structural component also comes into picture. The porosity which is generated is also advantageous. It is better. Why it is difficult to apply in structures, for example, ship and aircrafts. Super hydrophobic surfaces are very fragile, not very structurally sound. It is not possible for you to maintain them at certain angle with certain dimensions. They can be damaged very easily. They can be degraded very easily while subject to long exposure to flow or whenever you are handling them. Effect of seawater is highly corrosive. It also gives rise to fouling. Now, there are other issues also. For example, how do you maintain that a particular velocity profile? How do you maintain a particular boundary layer? But even if it is lost, it is possible for you to restore it. But the structural issues actually remains. And because of them, this technique has not been very successful when it comes to even the modern scale ship size. We can also think in terms of changing the chemical composition, changing the pH, again, just to see how hydrophobicity can be restored, can be increased or decreased. Now, think about in terms of gas restoration or changing the chemical composition. This also is something which is not really successful, but there are some results which are available. So I will just skip this. This is a concept which I was telling you that think in terms of two skins which are moving against each other. And because the two skins are moving against each other, then you have the frictional drag which is coming into picture. And people thought that if that is the case, then why don't we go back to the basic automobile science and see can we lubricate? So you have one skin, you have another skin, and in between two skins, you are trying to lubricate so that when they move against each other, they moved in a flexible, less viscous environment. In our case, viscosity is coming because of the seawater. So they said that let's take seawater, let's take the surface, and between seawater and surface, can we have lubrication? Lubrication by different means. And when it comes to lubrication, then they thought of okay, what are the possible ways by which we can lubricate? So one is obviously the bubble drag reduction. That means you have air bubbles, micro air bubbles, which are surrounding your entire hull. So now you have hull which is surrounded by micro bubbles, and micro bubbles are surrounded by the seawater. So between seawater and the structure, you have the micro bubbles. Then other argument came that instead of bubble drag reduction, let's think in terms of gas layer reduction. Let's generate a gas layer on the hull, and then you have a hull, you have gas layer, then you have seawater. So between hull and seawater, you have a gas layer. Then idea got extended further. Instead of saying that we have layer of gas, can we say let's have a cavity? Now the complexity level increases from A to B to C. For example, it is very easy for you to ensure that the entire hull is covered with bubble. It is slightly difficult for you to maintain the gas layer. It is also very difficult for you to maintain the gas cavity over the entire length. But all have been tried, all have been analyzed. So, first case, people have observed the interfacial structures, see the mono dispersion, see the poly dispersion, see the clustering. In the case of gas layer grade reduction, it is froth state gas layer, and then you have the film. That means it covers the entire length. KH instability waves and the gravity waves, depending upon what kind of gas cavity you want. Now, gas cavity drag reduction is function of Froude number, which is given by U divided by under root GL, and the length of flow configuration. That means at what length you want the cavity to be done. The Froude number, which is less and less than 1, that means much less than 1, the buoyancy will be able to stabilize the cavity. When the Froude number is greater than 1, in that case, there are waves generated downstream. And in that case, it will become complicated for you to maintain the gas cavity. Now, it's pretty simple. As I told you that from bubble to gas cavity, the complexity increases. And when you are dealing with systems which are inherently complex, you cannot use them with the structures like aircraft and ship, because aircraft is governed by the buoyancy, weight. Any minor change in buoyancy, these will just come down. Similarly, ship is supported by buoyancy. So in the first case, in the case of aircraft, you have the lift, which is supporting the weight. Any change in the lift, the weight will start coming down and the aircraft will crash. Similarly, when it comes to ship, you have buoyancy supporting weight. Any loss of buoyancy, any damage to the basic flow characteristic will start sinking the ship. So, in a sense, when it comes to the buoyancy, we think lift and buoyancy are compatible to each other, complementary to each other, because they play the same role in ship and aircraft industry. Creating a stable gas cavity is challenging, but if you can do that, very good. Backward facing steps help to form the cavity, but it is difficult for you to arrest it. And that's where we say that beach and arresters are needed at the cavity enclosure. Less gas is required if the cavity is stable. Experimental results, especially for gas cavity drag reduction, you see the structure which has been designed, which has been tested. The steps are of 7 inch. You have the injection slots, you have the floating plates, you have the pressure traps, floating beach, that is basically the arrestor side, few meters by few meters, velocity 3 meter per second to 7 meter per second. Reynolds number based upon the cavity length is 10 to the power 7. Stable cavities only between 4.2 to 5.4 meter per second. Larger air flux is disturbing the formation of cavity. 95% drag reduction over the cavity extent. That means over this length, the drag reduction is phenomenal, 95%. But as I told you that it is not so simple to maintain it over the entire length. So over the cavity length, the redact will reduce by 95%. Hull with bottom dish terminating in cavity locker, and that allows you to focus on design with high speed, presence of waves, which will not allow the cavity to become stable. In calm water and waves, it is applicable for very low Fruits number, zero point 0.4 to 0.65. Within this 0.4 to 0.65, you can aim for 25% drag reduction, 4% for power you have to allocate for air supply, and cavities are stable up to seawater, sea state 5. And remember that sea state 5 is very low. So we have sea states 5, 6, 7, 8, 9, 10. So normally we operate up to 6, 7, 8. 9, 10 is the only survival state. Higher drag reduction in waves. That means in wave, you really don't get any benefit. Implementation has been there for model scale and full scale. But the only issue is that the cavity are not stable. Cavities cannot be maintained over the entire range of Fruits number. They are applicable at a very low Fruit number range. But within this is the cavity length, ideal cavity length. So within this, you will feel that the reduction is 95%. And most of the hull is covered by the cavity lengths. Only these portions and these portions and these portions are without cavity. So you will find that the drag reduction is significant. So people thought that if this is not applicable, then what else? Forget about cavity. If you cannot generate cavity, can we cover the whole ship with bubbles? That is called bubble drag reduction. So you have structure, you have fluid. In between, you are trying to generate lubrication by using the bubbles, air bubbles. Further, looking into the issue, you have bubbles which are smaller than coherent structure. You have bubbles which are comparable to coherent structures. You have bubbles which are larger than the coherent structures. And different mechanisms for different bubble size is possible. This is a CFD simulation. And you can see that there is a low speed range, there is a high speed range, there is a low speed streak which will be generated, etc. etc. So depending upon the range of speed, depending upon what do you want, you can generate bubbles of different size. Different mechanisms involved. Bubbles will deform. Bubbles may break up. They will absorb kinetic energy and they will release the kinetic energy with time. They will damp turbulence. And the moment you are able to damp turbulence, you will be able to reduce the drag. Affect the coherent structures. It is difficult to keep bubbles close to the wall. Bubbles normally do not stick to the wall, they will have a tendency to move away from the wall. They are also affected by the fluid property, for example, density, viscosity. And they are also extremely difficult to generate because they consume a lot of power. And especially when it comes to micro bubbles, then the power consumption is slightly on the higher side. But they do offer significant drag reduction. And for this, we define what is called G, the gain factor. Percentage of drag reduction over what is called white fraction, because you are generating bubbles, so you have the white fraction. So you see here, we are looking for something between 1 and 5. Interfacial stability is here. Transition to gas stratification. Gas layer, pseudo turbulence, yielding spherical. So this is the something which we can aim for, which we look for. This is the flow speed in the bubble size. So roughly sub-millimeter size we are looking for. Roughly higher speed around 10 meter per second, basically 1 to 10 meter per second we are looking for. And we are not looking for micro bubbles because they add to the complication. We are also not looking for millibubbles and larger bubbles. So basically sub-millimeter size bubbles offer you a decent choice in prediction. Other argument was that why can't you use, instead of bubbles, instead of gas cavity, just a gas as a lubrication. So that's called air gas layer concept of reduction. So you have liquid, you have structure, and in between you are trying to ensure that you have a generation of layer consisting of air and gas. If you are consistent, then you may get a complete layer, or you may get the froths, basically the components. The bubble drag reduction is basically related to what we call air layer drag reduction. That means it is coming because just of the lubrication. High gas flux, that means percentage of drag reduction is a percentage of gas flux. So you see here, it touches from the traditional flux to the critical flux and it goes up to here. So starting with very low drag reduction possibilities, you have very high drag reduction possibilities. In general, it is important for you to maintain that this particular hull is surrounded by a particular gas, which is of very low density to start with. Second, it is covered entirely by that particular gas. So you have a gas layer which is covering the entire hull. So you have hull, you have water, and then you have gas layer. So now you think about it, you have one skin, you have another skin, and these skins, two skins are running against each other with a lubricating medium in between. Air layer, drag reduction, ALDR. The gas layer is occupying thickness, which is less than the boundary layer. Gas cavity is not directly linked to turbulence modeling. It is more to do with the slip length. Velocity fluctuations in normal direction is restricted. So the three-dimensional turbulence will reduce to two-dimensional turbulence, and you will have the reverse cascading effect. Cost of air flux, higher cost, ship draft. That means what is the draft of the ship available? What is the roughness you are looking for? What is the speed of the ship you have? So draft will push the cost, roughness will put the cost, speed will put the cost up. The ship length is something which doesn't affect the cost much, so it will lower the cost because it is always easy for you to maintain the gas and air over the entire length rather than only a very short length. So ALDR, that means the concept, is effective with vessels which have a flat bottom. That means the the structure at the bottom doesn't have curvature. Because if you have the curvature, then you will have the boundary layer separation. In that case, the bubble will not remain close to the surface or it will not stick to the surface. The surface will not be covered with the bubble. It will not covered with the gas. In that case, it will have a tendency to move away from the bottom. Full scale test has been done for a ship of 120-meter length, breadth of 21.4 meter, draft 4 meter, speed 12.4. And people have reported, the investigations have reported 11% drag reduction in the ballast condition, 6% drag reduction in the full loading condition, 7% to 4% energy saving. And you have the experimental setup here. You have the blower, you have the air pipe, and you have the bubble generators. And this ensures that it is covering the entire hull below. You have these two end plates, which will allow you to inject. So you have thrust 5% reduction, you have torque 5% reduction. That is in terms of power, K2 and K2. Air lubrication, that means instead of gas, can we just use air? It's a grand generic term for an extremely complex combination of different mechanisms of drag reduction. It should be noted that failures in drag reduction of ships were rarely published in journal articles. The author is aware of a number of failures in ship drag reduction via collaboration in private communication. But these are something which is not available in public domain. So when you have something which is available in the literature, always be very careful because that is something which is coming out at that level after maybe 10, 20, 30, 40 failures. So even if now it is available, now it is published, doesn't mean that if somebody want to replicate that or if somebody want to reproduce that, he will be able to do that. So all these drag reduction techniques are something which are highly engineering specific. Shape, size, combination, all these are important. And even if the concept is known, even if the concept's validity is known, proven, it is not possible for you to always design and fabricate the same concept within your mechanical and industrial expertise. That is something also we tell our collaborators, our scholars, our friends that even if you have a concept about which the science is known, the translating science to engineering is not really that simple. And many concepts will fail at that level itself. One more idea is that can you think of basic electromagnetic concepts? That means you have fluid. Can you charge the fluid? Can you change the basic chemical composition at the electromagnetic level? And that is which is more in magnetic levitation and all that. So, but you should know. And the idea is simple that you have electromotive force, which is also Lorentz force, between two poles, north and south poles. You have the flux density, and you can change this force between north and south pole, and it will affect your the flow, especially when it comes to the magnetic structures. What is the idea? Published physics of fluids around 20 years before. 40% reduction was reported. The issue in energy requirement is way too high, one order of magnitude larger. Drag reduction is the CFD analysis seen. Overview, when we lift the when we compare the lift buoyancy, support of weight, Reynolds number, Fruits number, everything. So couple of possibilities are there, which falls under passive drag reduction. Riblets and textured surfaces, large eddy breakup devices, super hydrophobic surfaces, compliant surfaces. They are under passive drag reduction. All of them have been tested, published. Some of them have entered into the engineering design. For example, the blades have entered the engineering design. Active drag reduction techniques, polymer injection, gas injection, Lorentz force, mass blowing and suction, wall motion and deformation, heating and cooling of surfaces, bubble gas reduction under gas and air layer drag reduction, gas and partial cavity drag reduction. Out of this, only the bubble gas reduction has been proven quite extensively, even at the full scale model. Other possible techniques which can be investigated in future, inspired by dolphin skin, you can think of wall mounted micro mini structures of the riblet form. Wall compliance will affect turbulence. If this idea can be utilized, compliant surfaces can be investigated further. You have mass addition to change the basic characteristic of turbulence. You can have some ways by which skin friction can be reduced by maintaining the flow in the laminar region only. Think of mass blowing and suction, wall motion and deformation, heating and cooling of surface. That means the temperature change. Experiments have been done for roll or summer. Again, the 65% drag reduction has been reported. In case of wall motion, wall deformation, that means flexible wall, can achieve approximately 40% drag reduction. But think about it, flexible wall motion deformation is not applicable to structures of ship aircraft kind. But for microstructures, yes, it is. The idea has some potential. Other possibilities, reduce the wetted surface area. That means you have a ship, utilize the artificial lift concept. At a proper lift provided by the aerofoil, the surface of the ship will come out. So you will reduce the surface area. So wetted surface area reduce, use of aerofoil, hydrofoils. Frequent hull cleaning, maintain zero fouling, maintain clean hull, use the robotic systems for hull cleaning. You can also use nowadays autonomous systems, autonomous vehicles for hull cleaning. Anti-fouling paints ensure zero fouling through cleaning and painting. Bio-inspired self-cleaning surfaces have been developed, are being investigated. Mimic shark skin, lotus leaves, etc., which were discussed right in the beginning. Conclusions. As an engineer, you should know what has been done. Some methods have been implemented. Riblets, air, layer drag reduction, quite successfully. Others are still in the lab. Experiment simulations have been reported extensively, primarily at low Reynolds number only. And most of the experiments are done in negligible pressure gradient. Scaling issue. We really don't know what happens when we scale from 1 meter to 100 meter. Frictional drag reduction may alter the form drag. That means when you focus too much on frictional drag, you may also affect the other drags, sometimes adversely. For example, you may promote to delay flow separation. So if you promote flow separation, you are basically paying the penalty. If you are delaying flow separation, you are better. Other aspects, energy savings, cost, maintenance, weight, all of them adds to the complication. And finally, engineering is about the cost. finding solutions with a reasonable cost, with less maintenance, less weight, with higher energy saving. So we'll close here. If you have any doubt, you can ask. Any doubt?
Sir, thank you very much, sir. You have taken 3 days, very long. Whole syllabus you have completed almost.
Yes.
Thank you very much, sir. Thank you so much.
It's my pleasure.
Anytime you please visit our NIT Andhra Pradesh, sir. We will invite you for offline also in your convenient time.
Sure.
I request, actually, sir has a very busy schedule. Tomorrow he has to fly. That's why we have shifted. And sir, he has very commitment that again he told tomorrow he can take from 9 o'clock to 11 o'clock. Then I requested him to take, and I requested another resource person. I request all the participants, if you have any doubt or you have any feedback or anything, you please talk. Without any hesitation, you please ask, so that because we cannot visit IIT Madras always in ocean engineering, but sir is live right now. Please, anybody.
Sir, good evening, sir. This is Rakesh Kumar.
Yes, Rakesh.
Sir, it's a general doubt, sir. Like, how about machine learning concepts fitted into this hydrodynamic design, like finding the optimizing characteristics of variables?
We need to understand one thing very clearly about machine learning. It's basically a tool. It's a tool of understanding the relationships where the science is not existing, where the math is not there, the physics is not there. So if you have a couple of parameters which are available to you and you really understand their scientific behavior, how they are linked mathematically, it is better for you to go with machine learning. The same is true for everything which is coming from the soft computing side. When the problem is ill-defined, when the problem is not really understood, in that case, it is always advisable for you to go with soft computing, machine learning, neural networks, genetic algorithms, etc., etc. The problem in the world of fluid mechanics, especially when it comes to drag, unless until you understand the science behind it, you cannot replicate that into engineering, because engineering is basically the physical transformation of whatever we understand the science level. So first you understand the science behind it, then you understand the engineering behind it. Get a sufficient number of parameters, number of parameter studies, and then you think of optimization. But the problem in this area is that, first of all, the science itself is not really well understood. As I told you before, even if the science is understood, when you try to translate the science to engineering at your scale, in your lab, it's not going to be easy. Because somebody may say that he has manufactured 1 micron riblet or 1 millimeter riblet of a particular shape, of a particular size, and it has been welded into the skin. The same if you do in your lab. Micron may become millimeter, the millimeter may become centimeter, so on and so forth. So that's the problem with drag reduction, because it's the problem of micron, micron level, not really a problem of meter level. So I am very kind of disrespectful towards soft computing, because it is applicable for a very narrow range of application, especially when the problem is ill-defined. But nowadays it has become fashion to apply machine learning everywhere. For example, people are solving linear programming problem also with genetic algorithm, which is fundamentally wrong. To understand this, that micro level problems, micro level organism, micro level mechanics is something which is difficult at the science level itself. Then engineering level is much more complicated. We have the manufacturing complexities, manufacturing limitations coming to picture. So think twice before applying machine learning models where sufficient science is not available, sufficient data is not available. You can ignore the science part, but at least the data should be available. Data can be available only when somebody is able to make the model, somebody is able to test it. And in this field, the tests are very limited. Except the top journals, for example, physics of fluids, experimental physics, JFM, you will hardly find like papers which are available. And they will not give you the data which you need for machine learning. So it is not really advisable to use machine learning for problems relevant to fluid mechanics.
Okay, sir. Thank you, sir. Sir, how about this dimensional analysis fitted into the scaling concept? We're talking about
Now,
scaling problem.
again, when we have a scaling effect, the more complications come because the nature of flow may be different. Because when we scale it up, the basic nature of flow will change. And that basic change in the nature of flow is difficult to entertain, difficult to understand, difficult to model. So, a lot of advantages have been reported, documented at the model scale. But when you try to replicate that on the full scale, even the concept stability will come under question. For example, I've explained about the gas bubbles, gas cavities, and all that. When it comes to slightly larger scale, even to maintain them is difficult. Then the speed is also important. Then everything is a function of density, fluid density, which also changes from one location to other location. So it takes a very long time, approximately 20 to 30 years, because the first major report was published in 80s when it comes to bubble, the gas bubble injection. And it was like first time went for sea trial only, I think, in 2015 or so. So think about it from 80 to 2015. That much years passed, people were not convinced that it should go for a full scale sea trial. Also understand the industry is conservative, aerospace industry is conservative because the investments are huge. And as told you, if something goes wrong with the lift, the whole aircraft will come down. Similarly, if something goes wrong with the buoyancy, the whole ship will sink. So industry will always look at the technology to get mature. And technologies don't get mature unless until you test them rigorously over a long period of time in different shape and different sizes. And the nature of flow is so delicate that the moment you move from micro to millimeter, the whole nature of flow will change. You may have a turbulent arrestor with micro riblets. The same will not work when you go for milli riblets. So it's all about Reynolds number and the effective velocity, which is a function of length and diameter. And once you change the effective length and effective diameter, Reynolds number changes. Everything else changes.
Okay, sir. Thank you very much.
Sir, thank you very much, sir. On behalf of our NIT Andhra Pradesh and Atal, two-week Atal FTP, and on behalf of AICTE and all the participants, thank you very much, sir.
Thank you.
Thank you for sparing your valuable time.
Thank
Sir, tomorrow or day after tomorrow, I will send one email to you, sir.
Sure.
Kindly sign and send it to me.
Thank you.
Thank you very much. And Dr. Santosh. Sir, thank you very much, sir. And this is also a vote of thanks to you.
Thank you.
So next time, any visit possible, you kindly make it convenient to
Fine,
visit
Ravi,
our native.
you can call me in future anytime whenever there's a need. It's our
Yes,
duty
sir.
to help each other. We are all teachers, essentially.
Yes, sir. Yes, sir. Yes,
It's
sir.
our duty. Thank you, sir.
Thank you very much, sir. Sir, thank you. Namaste. All of you can leave.